Welcome to lecture 24. This is the final lecture on virtual memory. We are going to be talking about ways to make adverse translation faster using a structure called TLB. A quick note on the final exam. So the final exam will be administered through Gradescope. We will soon release a practice exam to make sure that you're familiar with the interface. And regarding the topics, a strong emphasis would be placed on the topics that we covered after the midterm. So that includes pipelining, branch prediction, caches and virtual memory. We should have final exams on the website, which you can use as a reference to practice few more problems. Okay, so let's quickly recap the key concepts in virtual memory that we need for today's lecture. So virtual memory, like we talked about, is an idea that allows programmers to visualize and access a very large memory space. So from a programmer's point of view, which is defined by your ISA, in this example, the programmer gets to see 2 to the power of 20 bytes of memory locations, and that is because the virtual address is of size 20 bits. The physical memory, like we talked about, is defined by the computing system that you have. So your physical main memory may be much smaller than your virtual memory. So in this example, it has only 16 kilobytes. In addition, you may have allocated space on your disk, and that space can be changed by configuring your operating system. Now, at any given time, when an operating system is requested to create a process, it would create a new process, and as part of that process creation, it would create what is called as a page table. A page table is nothing but a data structure that contains a mapping between a virtual address to the corresponding physical address. Every process has its own page table, and that's how the operating system makes sure to isolate the addresses of different processes. So one process cannot access the physical memory that has been allocated to a different process. So today we want to focus our attention on this address translation process. So here I have a cartoon that simply represents how a virtual number is translated into a different virtual number, and like we talked about, the page offset remains a constant. So the address translation requires that you translate a virtual page number to the physical page number. Now, this address translation process has to be done for every memory access. Now, we need to make a memory access for every load and store instruction. So this will be done as part of the memory stage. But keep in mind that every instruction has to go through this instruction fetch stage where you retrieve the instruction from the memory. So you also have a memory access and in the fetch stage. Whether it is a load or a store or a branch or an add instruction doesn't matter. Every instruction has to come from memory, and therefore you need to access memory, and therefore you need to do an address translation. So in the case of a non-load or store instruction, you have one memory access through instruction fetch. In the case of a load store instruction, you have an address translation at the instruction fetch and one more in the memory stage. So the point is, the address translation is an important step that defines a process's performance. So what is involved in the address translation? Well, we said we need hierarchical page tables in the last lecture because we don't have space to have a single level page table. So in modern systems, you use at least 3 levels of page table. And so if you're going to use 3 levels, then to perform one address translation, you need to look into 3 different page tables, right? First level, second level, and third level. So 3 different page tables need to be looked up to perform one address translation. So clearly that is expensive in terms of amount of time that will take. In this example, for a single, even for a single level page table, you need to go to the main memory, and that could be expensive. So the main problem that we are going to talk about in this lecture is this problem of address translation overhead. Address translation is very important because it is on the critical path of an instruction's execution. It can be done only after the virtual address is known. Clearly, because you don't know the virtual address, then you can't really translate it. So you need to wait for the address to be known. So in the case of a load or store instruction, the execution stage is the one that would compute the virtual address. And in the memory stage, you need to then translate it. And the translation has to be done before accessing the memory hierarchy. Now later on we'll come back and optimize this particular constraint, but for now assume that you have to do the address translation after the address is known, and then only you can go and access the memory hierarchy, which includes your cache and then your main memory. And we just said that an address translation can be expensive, especially if you have a multi-level hierarchical table, because you need to perform n additional memory lookups. So what's the solution? Well, the solution is to avoid going to the main memory for accessing the page table. So we want to cache the page table. So we could just simply cache the page table in our regular caches. That's one option. But then we are going to pollute our regular data that the program is going to access, and maybe it is not specialized enough to exhibit good amount of locality for the page table that we want. So modern processors have a special cache called TLB, and that TLB is meant to cache only one data type, which is page tables. And it's meant to speed up the address translation by reducing the number of main memory accesses to page table. So it is, what is a TLB? Well, let's talk about that and then come back and talk about how large it typically is, etc. So this is how a page table cache looks like. So a page table cache, remember what a page table has. So a page table, it could be multi-level, but for now assume that it's a single level page table. You take a virtual address, and then you would have the physical page number that is stored in the page table, and that's what you want to produce as the output. So what we want in the cache is the physical page number. That's the data that you want to cache, right? And so that's exactly what we have done here. So we have the virtual page number that is indexed into this array, and then each entry in the array corresponds to an entry in the page table. Now what you will notice is that each entry has this thing called tag. Now this is effectively a very simple cache. If you go back to our first lecture on cache, we talked about tag array and a data array. This is way before we even talked about cache blocks, where we said for every address you keep its data item, and the address would be essentially what your tag is. So in this case, the virtual page number, the entire virtual page number, is treated as a tag, and the data item is just the physical page number, meaning just one data item. So if the physical page number is 2 bytes, then your cache block size is just 2 bytes, right? So in this case, I'm not really exploiting any type of a spatial locality at all, because my cache block size, TLB block size, is effectively just one page table entry. And there is also one more thing which is true, which is also true about the simple cache that we talked about at the beginning of the cache lectures, which is this structure is fully associative typically. And this allows a given virtual page number to be stored anywhere in the cache, and that's why we have the entire virtual page number as a tag, so VPN, and it can be stored anywhere. So that means when you do the address translation through TLB, you got to do a fully associative search, so you need a parallel comparisons to all the tags that are stored in this structure. Okay, so this is a very simple cache structure that caches different entries in the page table at the granularity of one page table entry. Now, you may be thinking about what happens in the case of a multi-level page table. Do I cache intermediate state of first level, second level, third level page table? Well, actually, the answer is much simpler. So you don't cache the intermediate page table entries, but you just store the final translation. So if you remember the lecture on hierarchical page table, what you do is first you access the first level page table, and then you access the second level page table, and then you access the last level page table. Let's say if you have 3 levels, and so eventually the last level, the leaf, would tell you what the physical page number is, and that's the answer that you're looking for to translate a virtual page number, right? So I'm not really interested in the address to the second level page table from here. I'm not interested in the address to the third level page table. What I'm only interested in is the physical page number. So this is what I need. Given a virtual page number, I need to translate that into a physical page number. All that hierarchical table allowed us to do is save page table space in main memory. It's purely a space optimization and nothing more, and we gave up by requiring more memory accesses to do that translation. But fortunately, when you have such a cache like TLB, you can get rid of those intermediate steps and simply cache the virtual page number and the final answer, which is the physical page number corresponding to that one. Right? So to summarize, a TLB is nothing but a fully associative cache. Each entry is a page table entry that translates a given virtual page number to a physical page number. And because it's a fully associative structure, it has to be fairly small. You cannot afford to have thousands of entries in it, because then your access would be much slower. And therefore, in modern systems, TLBs are typically small. It caches only 512 entries. Now you might be saying, well, that's too small. Then the cache hit rate may not be, or rather the TLB hit rate may not be high. But that's not really true. If you think about it, if I have 512 entries, that corresponds to 512 pages. So I can translate any address in 512 pages using just 512 entries in the TLB. And if I say each page is of size 2 to the power of 12, which is typical size of a page table in modern operating systems, which is 4 kilobytes, then this is a fairly large amount of address space that you're able to translate with a very small structure. And that's why even with the small TLBs, the TLB miss rates tend to be much low. Okay, let's go through an illustration to understand how TLBs work. So I'm also going to use this opportunity to illustrate how a process is created by the operating system and how it begins its execution. So when an operating system is asked to create a process, as part of that creation step, it would create a fresh page table for that process. And that page table would be initialized to all invalid entries, except for few entries that correspond to the instruction segment and the global data segment in the address space. So those pages would have pointers initialized to point to the corresponding data and instructions in the executable, which is stored on the disk. And we will see how that is done very soon. And then the process will be scheduled on the processor. The program counter will be initialized to the first instruction, and then the instructions will start executing. So now let's see how all this is stored in memory. All right, so now before the operating system starts a program, everything looks empty except for on the disk you have, let me bring my pointer here. So except on the disk you have the executable that is stored. So here I'm assuming that my executable is stored in 3 different pages. Text 1 and text 2 correspond to the instructions, and global data corresponds to the global data segment of that particular program. Okay, now let me explain all these different tables briefly so that you can follow the example. So of course this is the disk pages colored in blue, goes from the address D0 to D1003. Now this page again could be increased or decreased based on the user. It's a swap partition size, and it can also include non-swap partition if it comes to the data such as executable files, which is the case for this text and global data. All right, so the pink colored box represents the main memory. So this is your physical DRAM. I have 4 pages worth of space, and my yellow box is the TLB. This is the structure that we just talked about. It is a cache for page tables, and because it's a cache, it's located within a processor. So memory is located outside the processor. Disk is obviously also located outside the processor, but TLB is a very fast structure that is located within a processor, and it has only very few entries. So in this example I'm assuming 2. Each entry is a very simple data item. So this is a virtual page number and a physical page number. So it's not a lot of information here. It's just a few bytes worth of data, whereas these contain 1 page worth of data. So these boxes are not to scale. And so disk page is also 1 page worth of data. So typically this is 4 kilobytes, this is 4 kilobytes, and here we are talking about less than 4 bytes. So these are physical structures: TLB, main memory, disk pages. These are all physical structures that is located somewhere in your computer system. The ones that you see here, these are not physical structures. They are just, for example, the page table is a logical data structure that an operating system has allocated for this particular process. And the page table, being a data structure by itself, is going to be stored somewhere in the physical memory. And this references, it's an example that I'm going to use for illustrating how this whole system works. And the physical references is the reference or the address that I would get after translating these virtual addresses into physical addresses. So these are virtual addresses that are generated by the program when it executes in your pipeline. All right, now I'm going to also assume that the page size is 4 kilobytes and the page table entry size is 4 bytes, which is not going to be super important for this example, but it's important to understand that we need 12 bits for the page offset, because when you do the bit manipulation, that information is going to be needed. All right, so the very first step, when a program is loaded in memory, the first thing that the operating system, or one of the first things it does, is create a page table for this process. And like I said, the page table is going to be stored somewhere in memory. So in this example, I'm going to assume it is stored in M0. This 1 page is reserved for storing the page table of the process that the operating system just created. And like we talked about, the operating system initializes the entries that correspond to the instruction and the data segment, which are located in the executable when you start the process. So what D1000 says is my virtual page 0 is an instruction segments page, and it is located on the disk, which is text 1. And I'm going to mark it as read only because I don't want my program to change my instructions. This could be different for self-modifying code, but for now, this program doesn't change instructions, and so therefore for extra protection, we have marked it as read only. The second page, page number 1, virtual page number 1, is also a text segment. Again, it is stored on the disk. A pointer to it is stored in the page table. And the third page is the second, with virtual page number 2, corresponds to a global data segment. So if you go back to one of the earlier lectures in this course, we talked about how a program's address space is composed of instruction segment, data segment, and then dynamically created heap and stack. So what operating system has done for us is it has created all the instruction and the data segment, but of course it has not created the heap and the stack, which would be created on demand as the program executes. Now, let's say the program starts its execution. The very first thing that will happen is the first instruction needs to be fetched. So the address, let's say the operating system has initialized the program counter to 0. So now instruction has to be fetched, and that requires an address translation. So you would go and check the TLB. So the processor in the fetch stage would check the TLB for an address translation. The translation says, well, the TLB is empty, so it's going to be a TLB miss. So now the TLB miss handler would look up the page table, which is stored in M0 of the main memory. So this is a main memory lookup. Again, we are in the middle of an instruction fetch here. Because of the TLB miss, we have to do a main memory lookup. And that main memory lookup would allow us to do the address translation. And the address translation says, well, the instruction is located on the disk. So it's going to be a page fault. So I accessed the physical address 0 to do the address translation. Remember, 0 corresponds to this page 0 here, which stores the page table, and I access this address 0 to do the address translation, and I discover that it's a page fault. And so now I have to access D1000, and I access D1000 and I bring the data into the memory because I have free memory pages. So operating system allocates a new page, M1, and then changes the page table entry to reflect that fact. And now I would also want to cache this in the TLB so that in the future, if I were to access the same page, I don't need to go through this TLB miss handler that would require me to access the page table in the main memory. Okay. So now let's say that now that I have loaded the text 1 into my main memory, now I can service the original instruction fetch by accessing the main memory. So the main memory physical address would be 1, which is the most significant hexadecimal digit, followed by the page offset for this is going to be all zeros. Remember, our page size is 4 kilobytes, which is 12 bits for the page offset, which translates to 3 hexadecimal digits. So the page offset comes from the last 3 hexadecimal digits from the virtual address, and I have that same thing here. So you need to convert it all into binary format and then concatenate the page offset to the physical address page number to get the full physical address. And in this case, I'm able to do that very easily because my 3 last hexadecimal digits need to be concatenated with this. So it's easy for me to just work in the hexadecimal space for this example. All right, so now I got my physical page number 1 because that's where my text 1 got stored in. So virtual page number 0 is being translated into physical page number 1, and that is what I have cached here too. Virtual page number 1 is translated to physical page number 1. All right, so now let's go and execute the next instruction. So the next instruction, the PC would have been incremented by 4, and so I'm accessing the next instruction, which is 004. And because we had already done the hard work of bringing the text page and doing the address translation and caching it in the TLB, we don't have to go through all that again. The TLB has the address translation for us. It says 0 page number has to be translated into physical page number 1, and then we can slap the offset to the end, and then we get the full physical page number, which is 1004. And so this is not a page fault, because again we have brought the page to the main memory before, and the corresponding address 1004 would be accessed, and then you can go on from there. Now I'm ignoring the processor caches in this whole picture, but if you did have a processor cache, then address 0 and 4 would be part of the same cache block, most likely, because block sizes are larger than 4 bytes, and so it would have also been a cache hit. But we are ignoring that detail now because our focus is to simply understand how the TLBs and the page tables work. Okay, so now let's assume that this second instruction is some form of a memory instruction. It could be a load or a store, we don't care for this example. And what that means is that it would generate a virtual address as part of that load or a store, and that address need to be accessed, the memory has to be accessed in the memory stage of that instruction. And so that address happens to be, the virtual address happens to be this, 7FFC. Of course, there's no entry for that in the TLB. The virtual page number 7 does not exist in the TLB, so it'll be another TLB miss. So this is our second TLB miss. And in this case, it's going to be slightly different from how we handled the first one, because if you look at the page table entry for the virtual page number 7, there is no map. So unlike the first TLB miss, where we did have a pointer to the disk, meaning the data existed before, even though it was a page fault, the data existed on the disk. This page fault is different because the data doesn't exist at all. This is the first time the process is interested in this page and no data has been created for it. Okay, so maybe this is a store instruction that is trying to store data into this new address that has never been accessed before. All right, so what does the operating system do? The operating system says, oh, well, this is a no map. Fine, I will allocate a fresh new virtual page for you, sorry, physical page for you. And let me say that page happens to be M2. And then from that point onwards, it works as in the case of the previous page fault, where M2 is allocated a fresh page, and the translation for that page is stored in the TLB. So 7 translates to 2 in the physical address, and then the physical address 2 followed by the page offset is going to be accessed. Now, one detail that I missed is when the operating system creates a fresh page for a no map entry, there is no data to start with, so it has to initialize it to something, and typically they would initialize it to all zeros. Okay. The other bit that is different about this page is that it has read and write permission. That's why it's R and W. Previously, because it was an instruction page, we had it set to read only, meaning we didn't want the instructions to be modified. Okay, so now let's go and execute the third instruction. Again, now it's going to be the instruction fetch that increments the PC by 4 from 4 to 8, access the TLB. Each page is of size 4 kilobytes, so this instruction would be part of that same page, so it's a TLB hit, and we go through the same process like we did before, where we go and get the instruction. That's no different. Now let's assume that this instruction is also either a load or a store instruction, and in this case the address is different from the previous addresses. Not only that, it's to a virtual page that is different from all the previously accessed virtual page. So before we had accessed the virtual page 0 and 7, and this one is going to be to 2, which we don't have in the TLB, and it's going to be a miss. What do we do? Well, the same as what we did before, which is to go to the page table and check whether there is an entry. Well, in this case, even though this is a data access, there is an entry for it, and it's on the disk. So it is a page fault, but this page fault would require that I go and access the global data segment, and then the global data segment would be brought back into the main memory, and then a corresponding entry would be allocated in the TLB as well. So remember that our TLB was full, and so we had to find, let me go back to the previous slide. So before I had 0 and 7, now I'm bringing in a new entry. I don't have space for it, so I have to evict one of these two entries. I've been accessing 0 a lot, so that's clearly not released recently used entry because we just accessed a 0 entry, right, for the instruction. So according to LRU, I would have to evict the virtual page number 7's entry and replace it with the one that I just accessed. And then this was accessed, allocated to the physical page number 3. So 3 followed by page offset is my physical address that I accessed. So far, we've kept caches out of the virtual memory discussions, but now we're going to bring them back into the picture. And it turns out that there are a couple of different ways in which I can integrate caches with virtual memory. And they have a few trade-offs which are interesting, and we will go through them. So the main difference is in terms of how and when the address translation is done using TLB. And so therefore it's worthwhile to understand address translation's importance a little bit. So address translation, like we discussed before, is done for every instruction fetch, meaning for every instruction you need to fetch the instruction from memory, so you need to do the address translation. The instructions that are load or store, you need to do another address translation in its memory stage. So now when to do the address translation? Well, you can do the address translation only after its virtual address has been computed. So for instruction fetch, it's been computed and kept in the program counter, so that's not a big deal. But in the case of a memory access for a load or a store, you can't do the address translation before the execute stage, because that's when the virtual address gets generated. So now after the virtual address has been generated, what do I do with it? Do I go and directly use it? Do I use a virtual address to access the cache, or do I use the physical address to access the cache? And that has an important implication on performance. So now let's take the simpler option first, or more intuitive option, which is the CPU generates the virtual address either in the instruction fetch or the memory stage, doesn't matter. You get the virtual address. Before you access the cache, you do the translation. You look into the TLB, which is effectively a cache for page tables. If it's a hit, you're done. You get the physical address, go access the cache. Well, if it's a miss, you have to go to the main memory, look up the page table, and then do the translation. It will take much longer, but hopefully that doesn't happen very frequently. So, but the main thing to understand here is you take the virtual address, do the address translation, and use the physical address to access the cache. And if it's a cache miss, you go to the main memory and you bring the cache block into the cache. Now here's an important thing. You store that cache block at a place in the cache that is defined by the physical address. So the tag, set index, and the block offset, they're all going to be defined by the physical address. So the set index would be derived from the physical address, the tag would be derived from the physical address, and so the next time when you want to look up the same cache block, you would be able to find them in the right spot. Okay, so now the implication of this design is that for every address that need to be accessed, I need to do the address translation, right? Because I cannot access a cache without the physical address. So first I got to do the address translation. So we'll discuss the trade-offs a bit later, but there's a more efficient way to design this, which is as follows. So instead of addressing the cache using the physical address, I'm going to use the virtual address to address the cache. Well, how is this going to work? Well, it's worthwhile to think about what happens on a cache miss. So let's say the first time I access an address, the cache doesn't have anything, so it's a cache miss. So I do the address translation. So maybe I'm lucky and TLB has an entry and I'm able to do the address translation, or if not, I go to the page table which is located in the main memory and do the address translation. But the important thing is, on a cache miss, I do an address translation and then go and access the memory. I bring back the cache block, store that new cache block in the cache. Let me get the pointer here. So store the new cache block in the cache such that the tag and the set index are derived from the virtual address. So this is the first time when I have accessed this cache block, and I'm going to store it in the cache at a place and tag as defined by the virtual address. So the next time I have to access the same address, I would be able to go and find it using the virtual address. I don't need the physical address to find it because I kept it with its virtual address tag, not the physical address tag. And so this is beautiful because now if there is a cache hit, I don't have to do the address translation at all, because CPU generates the virtual address, you go and access the cache, and you're done. It's only when there is a cache miss you have to go and do the address translation. So as you can imagine, this design can be faster than physically addressed cache. Then what's the problem? Well, we'll see in a moment that it can have some higher complexity when it comes to implementing context switches and ensuring process isolation. So this is another way to visualize the difference between physically addressed cache and virtually addressed cache. So this is an often source of confusion because in both cases we are talking about the same cache, and the only thing that is really different about the two designs is which address you choose. So in the case of physically addressed cache, I'm choosing to derive the tag and the set index from the physical address. Okay, so I take the virtual address, do the translation, get the physical address, and then I can figure out what my tag and set index is. So then I take these two values, go into the cache, look up the right set, and then do the tag comparison. In the case of virtually indexed cache, I don't need to do the address translation because I'm keeping track of everything in terms of the virtual address. So I take the set index and tag from the virtual address, and then I go and access the right set and then get the tags and then do the right comparison. Now maybe you have already observed this, but think about a question here. Would the tags be smaller or bigger for virtually addressed cache? Well, the answer is, for a virtually addressed cache, the tags will be bigger because the virtual addresses are going to be bigger than physical addresses. So it's the same data that we are storing, but we have the option to index it with the virtual or physical address, and they have some trade-offs. All right, so let's summarize the two designs before we evaluate the trade-offs. So in the case of physically addressed cache, get the virtual address. In both cases you get the virtual address, but in the case of physically addressed cache, you do the address translation. Here I have simplified it and said, well, look into the TLB and you'll find the virtual address to physical address translation. You take the physical address and then go and access the cache. If it's a cache miss, then go and access the main memory. You already have the physical address, so nothing else to be done between these two operations. The main thing that is different about virtually addressed cache is you do these two steps in the reverse order. So you take the virtual address, you can right away go and access the cache, and only on a cache miss you have to bother about doing the address translation by accessing the TLB. And then you go and access the main memory, because main memory can only be accessed with the physical address, because when we say physical address, we are referring to an address in the main memory. Okay, so now let's take a look at the trade-offs. Like we said, physically addressed cache can be slow because you always need to do the address translation and then get to the cache. And virtually indexed cache, on the other hand, can be faster because you can skip address translation for most of the memory accesses as long as it's a cache hit. The other subtle problem, which is a little bit challenging to understand, and we'll consider an example for it, is that physically addressed caches can be a bit simpler to implement for context switches, and it's more complex for virtually addressed caches. All right, so why are physically addressed caches slower? Well, it's slower because you can access it only after getting the address, and it's also inefficient because you have to do this address translation for all memory accesses. So that's kind of bad from the perspective of power and energy of the processor as well. And virtually addressed caches is very nice because I can skip address translation for as long as I have a cache hit. It's only when I have a cache miss I have to do the address translation. So I save a lot of TLB lookups, and therefore I save a lot of power and energy. What's the downside of virtually addressed cache? Well, we need to think about process isolation and what that means for cache design. Okay, so let me construct a very simple example here. So let's say I have two processes. So like we said before, whenever a process is created, the operating system will go and create a page table for them. So I have a page table for a process A, a page table for process B. Now, let's say I have a virtual address 10, and I can have a virtual address 10 in both processes, because keep in mind that virtual addresses are defined by the ISA. So A and B can both access virtual addresses that range from 0 to 2 to the power of 64 in the case of a 64-bit ISA. Now, the way these two guys, A and B, these two processes are isolated from each other is by the operating system, which ensures that it allocates a page for process A and a different page for process B, even though their virtual addresses are the same. So we talked about this in the case of virtual memory design. So let me call this address to be 100 and this address to be 200. Okay, so same two virtual addresses are mapped to two different physical addresses, and that's exactly what we want, because we don't want Chrome to be accessing Microsoft Windows's data when I'm running both of them simultaneously on my computer. All right, so now why does this matter for a cache design? Now let's think about what happens inside a CPU where there is a cache. I'm going to represent cache as a simple box. So this is my cache. So imagine the operating system has scheduled the process A on the processor CPU. Assume that there is only one processor core and that one is running process A. So obviously process A data will be allocated and stored in the cache. So let's say process A had accessed address 10. Now for the moment, let's assume that we are thinking about physically addressed cache. Okay, so I'm going to call it as a PA cache. So in the case of a PA cache, if A accessed address 10, I'm going to store that as 100, right? Because it's physically addressed, and that's how I keep track of it. The tag will be derived from the address 100. Now let's say the process A is context switched out. It runs for a while. After a quantum of time has passed, operating system will come and say, okay, you have had your turn, but now it's B's turn. So now B will have to start executing. Now when B executes, let's say B also wants to access virtual address 10. That's fine. But in this case, B will map to address 200, which is also okay because I'm using 200 to check the cache, and I will find out that I don't really have the data, so I will be a cache miss, and I go and get the address 200's cache block, and I store it separately in the cache, or maybe it will kick out 100. I don't really care. But the point is, B can recognize that the virtual address 10 is not there in the cache because it gets translated into the physical address first, and then you go and check the cache. Now, as you could have guessed, this whole process breaks if I use a virtually addressed cache. Now let's go through the same example, but with a virtually addressed cache. So I'm going to make this VA cache. Let's go through this example again. So let's say I have A running first, accesses the address 10. Now this is VA addressed, so therefore I have to keep track of it as in terms of virtual addresses. So when A accesses 10, I bring the cache block, no big deal, it uses it. Now let's say there is a context switch. So when there is a context switch, B comes in, starts executing, and like I said before, B also wants to access the virtual address 10. And in the case of a virtually addressed cache, remember we don't do the address translation when we access the cache. So you take the address 10, go and check the cache, and what do you find? Well, B finds that the address 10 is actually in the cache. Just a surprise, because this is the first time B is accessing the address 10. It should be a miss, but it's not. It's even worse because B is now able to access the data that A was operating on. So the entire idea of isolation breaks in the case of virtually addressed cache. Okay, so what's the solution? Well, we got to ensure process isolation. That's not a choice we have. So the only solution then is to say when A was running, it can use the cache as much as it wants, but when the operating system context switches the process out, the virtual cache needs to be invalidated. What does that mean? It means I want to go and mark all the blocks as invalid. Wait a minute, so if I mark them to be invalid, then I will obviously lose the data in the cache. So therefore I need to make sure that whatever data that is there in the cache, if it is dirty, I have to write it back into the main memory, which is okay because it will be stored in a spot that is different from the spot that B is using, which is over here, right? So A will write back the data to main memory at physical address 100, safely storing its virtual address data, right? And then it can basically completely clear the virtual cache so that B can come in and start using it. And B can go and use it for 10, and it will check that, oh, the virtual cache does not have the address 10, which is great, which is what we want. And then it can go and start using the cache and bring the data from physical address 200 into the cache. And then when it gets context switched out, it has to do the same thing, which is evict all its dirty blocks and wipe out the cache state so that the next process can use it. So the big takeaway here is that when there is a context switch, in the case of physically addressed cache, there is nothing to be done. Everything works beautifully. There's no problem. However, if you're using a virtually addressed cache, you have to clear it up because we cannot distinguish between the same address that is generated by two different processes. Two addresses mean different things for two different processes. Two different virtual addresses mean, the same virtual address means two different things for two different processes. So therefore, on a context switch, you have to clear the cache for virtual caches. And that's a problem because it adds a bit of complexity. And if the context switches are more frequent, so for example, in mobile phones and desktops, when you have a lot of interactive applications, you keep switching between one application and the other, context switches can be frequent. So in that case, you are clearing the cache too often, and that can lead to poor cache miss rate because you'll have more compulsory misses. Because every time you context switch in, you're going to bring all the blocks in, whereas if you did not clear the cache, then you can enjoy a little bit more temporal locality, because if the process B did not kick A's data out, then if A is switched back in, so if I schedule A and then B and then A, now if B did not clear the data, then A would be able to reuse the data that it had in the cache. But in the case of virtually addressed cache, when I context switch to B, everything gets knocked out. And so when A comes in again, there's nothing in it, nothing in the cache for it. So everything has to be populated again. So that's a trade-off. But in most like in supercomputers or even in data centers, when programs run long enough, context switches are fairly infrequent, and so there is not a lot of performance to be gained because you have a physically addressed cache. So what do we really use today in modern process? Well, for level 1 caches, again, if you remember our cache discussion, so CPU has multiple levels of caches. There is a small L1 cache, and then much larger L2, and then even larger L3. All these levels of caches exist because L1 is much faster, L2 is a bit slower, and this one is even slower, 50 cycles or so. And so L1 has to be super fast. So if you want something super fast, you want to do as less work as possible. And so we want to not do the address translation before accessing L1. So therefore L1 caches are typically virtually addressed. However, but L2 and L3 are physically addressed, so that when you context switch processes out, you retain some data, and also you don't have to incur a high latency for a context switch, because writing back the data from L2 and L3 will be much more time consuming, because obviously you have more data in L2 and L3, so it takes more time to clear them up. L1 on the other hand is much smaller, so it's kind of easier to clear them up in a quick time. So I would like to fill in a little bit more details about virtually indexed cache and physically addressed cache. Just the workflow and the latencies a bit more. There are a couple of points that I didn't make before that I want to make and wrap this up. So in the case of a physically addressed cache, you take the virtual address, you check the TLB. TLBs are really fast, so it takes about a cycle, and then you access the cache. If it's L1, you're talking about 1 cycle. If it is L2, level 2 cache, it could be tens of cycles. And then if it is a hit, you return the data to the processor. But in case if you couldn't translate using TLB, then you have to look up the memory and do the address translation through the software page table. And that can take hundreds of cycles because you're looking up the main memory. And so if you find the page to be valid, then again it will be only hundreds of cycles. But if the page is not valid, then you may need to go to the disk, and so then page fault handler needs to be invoked, which would bring the data from the page and update the main memory and the page table and the TLB, and only then you would be able to go and access the cache. It seems like you would spend a lot of time doing this page table lookups and disk lookups, but keep in mind that TLB misses are very rare, very, very rare. So the most common path that you take is TLB access, hit, cache. Most of the time it's a hit, and you return the data. And now if you don't hit in the cache, again you go to main memory, but you already have the physical address, so nothing else to be done. And let's go through the same details for virtually addressed caches. So you get the virtual address cache. The big difference is you don't have to do the address translation. Instead, you directly access the cache, which can be again 1 to tens of cycles depending on the size of the cache. If it's a hit, nothing to be done. Return the data to the processor. Address translation doesn't even come into the picture. But if it is a cache miss, then you have to check the TLB, do the translation. If it's a TLB is a miss, then you have to go to the main memory and then do the page table lookup and then do the translation. And then once you have done the translation, then you go to the main memory and get the data, and then you update the cache. So the other detail that I skipped over before, and it's useful to understand, is in the case of a virtually addressed cache, you have a couple of options as far as when TLB is accessed. So the design that we have been talking about is, well, take the virtual address, access the cache, and do the address translation only on a cache miss. But another option is do the TLB lookup in parallel with the cache lookup. Now, why would that be interesting? Well, if you were to do that, then by the time when you discover that the cache doesn't have the data, meaning it's a cache miss, then you already have the physical address to go and access the main memory. So you kind of shave off a few cycles when you want to go and access the main memory. But the downside of this design, and that's why we didn't talk about it earlier, is you're accessing the TLB all the time, even on a cache hit. And that's not an efficient design, because in modern processors, energy and power are super important. And so if you're going to wastefully access TLB for every memory access when you really don't have to, then that's not really an efficient design. But that is a design consideration that you may want to consider. Okay, so one final point I want to make is that an operating system provides few more extra features for supporting virtual memory. So in particular, it must be possible only for the operating system to change the contents of the page table. Because remember, page table is how you ensure isolation between the processes. Each process has its own page table, and page table allows you to do the address translation. Now, if user level processes like you and I, who writes a program and runs it on a computer, if we can change the page table, then we would be able to go and access any other program's data, and that violates isolation. So all the changes to these structures can be made only by the operating system. And so in order to make sure that our processes, the programs that you and I write, doesn't modify the page table, operating system has different levels of privilege modes. So it has a kernel level or a supervisor level or a executive level permission mode. So if you're running a particular program under this level of permission, that means a load or a store can access the page table, right? So the certain pages will be marked as kernel mode only pages, and so those kernel mode only pages, meaning belonging to the page tables, can only be accessed and modified only when a process is being run in the kernel mode, and the operating system will let a process to run in the kernel mode only if that process belongs to itself, like page fault handler, for example. And if you and I were to run our own programs on computer, let's say I wrote a program to sort a function and run it on a computer, so that program would run under user level permission, meaning I can do what I want to do with my program, but I won't be able to change the contents of the page table, either mine or other processes. Okay, so for more details on how operating system implements these features, I would encourage you to look up these links, which I have included in the slide. If you want to go deeper into these topics, you should do that. Or if you really want to, if you're really interested in virtual memory and operating system related topics, 482 would be a good choice for an upper level elective.